Like cells in series, one can also connect cells in parallel. Now if you take a module like this, and let's say we would like to connect this module in parallel with another PV module. Completing the circuit, the parallel connection of two cells or modules is like this. So you have module 1 or cell 1 connected in parallel with module 2 or cell 2 and in parallel with an external load or not. Let us call the voltage across the output terminal as Vt, and let us call the current that flows through the external load as I. Now these two are the parameters of importance, and we would like to know what is I versus Vt or I versus V. So this is what we would like to see for the system of cells connected in parallel. And here you have individually this current as I1 and current from panel 2, cell 2 as I2. The conditions here, I is equal to I1 plus I2. If I say that the voltage across panel 1 is Vt1 and voltage across panel 2 as Vt2, then Vt1 is equal to Vt2 is equal to Vt. These are the constraints, two constraints that are applicable for cells connected in parallel. This is constraint 1. The terminal voltage is equal to the voltage across each of the cells or modules connected in parallel. This is 1. The other one is summation of the currents from each of the panels will add up to the terminal current. This is the second constraint. I can replace the PV cell symbol with the current source diode model, the idealized current source diode model, so that we will be able to understand the operation much better like this. Completing the replacement, we see cell 1 replaced by the current source and this red colored diode, cell 2 replaced by this current source and the green colored diode. This is paralleling two PV cells in parallel along with an external resistance R0 which acts as the load. This is the circuit of two PV cells in parallel. Let us zoom in, and it is clear that we have these two cells, PV cell 1 and PV cell 2, in parallel with the load R0. This here is I1, which is the sourcing current from cell 1. I2 is the current from cell 2. I1 and I2 add up to give you I, which flows through the external load R0, and Vt is the voltage across the terminals of the parallel cell system. Now in order to study and see how we can get the IV characteristic of the entire parallel connected system, let us draw the x and y axis. X axis is the voltage axis, which is the terminal voltage. I axis is the current, which is the terminal current axis. On this, let us superpose the IV characteristic of cell 1 and cell 2. Right now I have taken identical cells and therefore they have identical characteristics, and therefore this is actually two characteristics superposed one upon the other. Now these two characteristics have these parameters. One is ISC1 and ISC2. This is the short circuit current point for both the cell 1 and cell 2, and this point is the open circuit point for both cell 1 and cell 2. From constraint 1 of cells connected in parallel, we saw that Vt is equal to Vt1 plus Vt2. This point here marked blue, this operating point is obtained when the current is 0, which basically means when R0 is made open circuit, there is no current flow, and therefore that would be the x-axis line, and this is the operating point under open circuit condition. Under that condition, we see that as the cells are in parallel, VOC is equal to VOC1 is equal to VOC2. Now let us get a second operating point, and let us get that by short circuiting R0. So when you short circuit R0, we are talking of the y-axis. 1 by R0 is infinity. And there we apply the second constraint where I is equal to I1 plus I2. So when you short circuit, ISC will be equal to ISC1 plus ISC2. So that would be the second operating point. We have these two operating points. We can smoothly join this and get the equivalent parallel cells IV characteristic. Before that, let us see what happens when you pan the load line 1 by R0 line from the short circuit condition down to the open circuit condition. So if you take one arbitrary load point and corresponding load line like this, the R0 is now finite, not a short circuit, nor is it open, and the load line is like this. This is the operating point. The current here is basically this height. You see that this arrow having I1 comma I2 of these two identical cells is the current at this point vertically, and you just add it up, I1 plus I2, and you will get the current at this operating point. And this distance is the voltage, which is the terminal voltage also, and to across both each of the individual cells. So that is Vt. So if you keep on panning this line down to the condition where it is horizontal up to the open circuit point, you will get the entire set of operating points, which the locus of which will form the IV characteristic of the parallel connected cell system. So this dark green line is the IV characteristic of the parallel connected cell system.